All right, class, we're gonna get started. All right. So today we're gonna pick up where we left off on Monday, talking about basically friction factor in internal flows. We're gonna solve the laminar part of the Moody diagram today. Before I get started, just a few announcements. Homework 6, right, it's Wednesday. Homework 6 due today, the one that was assigned just before break. Homework 7 will be assigned today. So homework 6 due, homework 7 assigned. Midterm 2 is coming up. This comes quick. So I just wanted to make sure to remind you of this. Midterm 2 is scheduled for Friday, November 4th. That'll again be in class. By then we will have covered chapters 5 and 6. So that midterm is mainly going to be testing concepts from chapters 5 and 6. But remember, we opened class on Monday by talking about how up till this point, we've basically been developing tools. Right, chapters 1 through 4, we were developing tools. Actually, 1 through 5, we've been developing tools that we're using now in chapter 6. So we are going to use information and tools from chapters 1 through 4 in the exam that is primarily testing chapters 5 and 6. Okay, so like I still expect you to know what a Newtonian incompressible fluid is, right? Even though that's a concept from earlier in the text. And then in response to a suggestion by you, I added some more detailed reading suggestions for at least for chapter 6 so far on the syllabus. So it's kind of broken down by section that I intend to cover each day, rather than just a chapter for a big chunk of material. I'll go through and try to remember to do that for for the rest of the material that we have as well. Any questions before we get started? Okay. All right, so last time, this is where we ended. So we said that we have, so we used basically a momentum balance. We looked at a relationship from the 1800s that told us, or that was based on the observation that the friction loss within pipes tends to go as V squared, LV squared over D. And from that, Hagen proposed a friction factor definition, which tells us what the head loss is in the pipe in terms of V squared L over D and this friction factor F. And so the right, F is equal to H, L V squared over D times 2G. And we said that we basically have reduced then the problem of finding H, the head loss across a section of pipe, to the problem of now figuring out what F is. And then as long as we know L over D and the velocity, then we can figure out the head loss across that pipe, or the loss in energy across that pipe. And we use some scaling analysis, right, to figure out what are the important non-dimensional parameters that govern this problem. We determined that there were going to be 3, and they are, we wrote them down as this friction factor F, which is non-dimensional, Reynolds number, our old friend, is non-dimensional, and this epsilon over D, which is the relative roughness of the pipe. So epsilon is the roughness of the pipe material. So think of it as like the texture of the wall of the pipe. This table has a texture to it, probably a roughness of about 1 millimeter or so, that I can actually feel. And so if we have a flow inside of a pipe, which is really what we're concerning ourselves with in this chapter, then relative roughness is the roughness, the texture of that wall, divided by the diameter of the pipe itself, and that determines our third parameter. And now if we take real data and we plot it in terms of these non-dimensional parameters, this is the set of curves that we get captured on what we call the Moody diagram. And we can see different behavior at low Reynolds numbers, up to Reynolds number of about 2000. This is the laminar flow regime. Then we see in this higher Reynolds number regime where we have turbulence. One of the, and then we have this kind of intermediate regime where things get messy. One of the key features here is that this epsilon over d, this roughness, you can see that it matters a lot in the turbulent regime. And we're going to talk a lot about roughness in the turbulent regime when we're talking about turbulent flow. Because so in this regime, there's not just a single curve, right? There's a whole family of curves describing friction factor versus Reynolds number as a function of this relative roughness. This is relative roughness corresponding to each one of these blue lines. It's read up on the right-hand side here. But in the laminar flow regime, you'll notice there's only one curve, right? And that's because the impact of roughness is negligible in the laminar flow regime. So today, as we're going to go through and develop an analytical solution actually to a friction factor within the laminar flow regime, we're not going to include roughness because over a century of data tells us that the roughness is not important within the laminar flow regime. So we're just going to get a single curve, and we're going to return to understanding things about roughness or talking about roughness when we get to turbulence. So that's where we're headed. Any questions on this? Our orientation, where we're going, what we have to do? Yes. Yeah, non-standard pipe. I don't know if you had a, some crazy low design of pipe, or really more realistically, some kind of new fitting or something that you want to understand, and you're trying to design a new fitting for, or a new valve design for lower pressure, or validate a new valve design for application with some new fluid or something. Then you might address that computationally. Yeah. Yep.
So kind of on that same topic, so like I guess so the pipes out of the grenade, does it also work like slightly pipes?
Yeah, we'll talk about non-circular pipes after we've gotten a handle on circular pipes. We'll talk about what we can do for non-circular pipes. So for turbulent flow, what we'll see is that the things that we're learning pretty much just will apply for non-circular pipes. We just have to make a little adjustment to how we compute the diameter d. For laminar flow, the solution that we're going to go through today is for a circular pipe only, and it doesn't really hold. There's some substantial error if you try to use it for like a square pipe or a rectangular pipe or something. Yeah. And actually, for laminar flow, we're going to do the solution analytically for a round pipe. So we're going to work with Navier-Stokes in cylindrical coordinates today. But you can also derive analytical solutions for laminar flow through a square pipe or rectangular pipe, that kind of thing. Those solutions are definitely beyond the scope of this class, but the results of those solutions are not. But we will talk about that later. Yeah. Okay. Other questions? Okay. All right. So let's get started on figuring out where the Moody chart comes from, starting with this laminar flow regime. So the central question here is we want to know the friction factor F, right? We have our relationship here, basically our sort of empirical definition of F, right? That comes from 1850s, saying that the head loss due to friction in the pipe, we're going to write as F L over D V squared over 2G. Right, and again, remember in this chapter, our main task is finding HF, but here we've just kind of kicked the can down the road and lumped all the stuff that we don't yet understand into this parameter F. So today we're going to get started on that parameter F for laminar fully developed pipe flow. And we want to derive, we're going to derive the velocity profile for laminar fully developed pipe flow. We're going to see that it's parabolic, just like it was for flow between two flat plates, which you did on homework 5. And then from that velocity profile, we'll be able to extract other important parameters, including what we need to figure out F for laminar flow. So we're looking at laminar fully developed pipe flow. Remember, fully developed. What does fully developed mean? Yeah. No change with respect to X, right? So ddx, partial derivative of velocity with respect to X is equal to 0, is the fully developed condition. What that implies is that if my velocity profile, let's say, looks like that, we're going to get a solution that looks just like that on the upper right. If it looks like that at this x position, and I go down here at some other x position in the same pipe, same diameter pipe, I'm going to have the same velocity profile because there's no change in the velocity profile with respect to x, right? And fully developed says it doesn't matter how long my pipe is, right? That pipe could be a kilometer long, and I would have the same velocity profile once I'm in the fully developed region, right, which is like 16 pipe diameters in or something, so relatively short distance from the start of the pipe. So once I'm in fully developed region, that velocity profile is unchanging down the length of the pipe. So to start, we're looking at laminar fully developed pipe flow. We're going to make some assumptions here in order to simplify the problem. First, we're going to assume that the velocity in the theta direction, the velocity like swirling around the pipe, is 0. And the velocity in the in the radial direction, the velocity coming out from the center of the pipe, is also 0, meaning that only Vx, only the velocity down the pipe, is non-zero. We're going to assume that it's fully developed. So the partial derivative of velocity, this is vector velocity, with respect to x is 0. For now, we're going to be neglecting gravity. We'll put this back into our energy balance, but it's not going to have an impact on the shape of our velocity profile. We're going to assume steady state. So the partial derivative with respect to t is 0. And we're going to assume axisymmetric, meaning that we don't have any variation in the theta direction. So going around the pipe, right? So theta is the coordinate that's going around the pipe. And we're going to assume that all derivatives with respect to that are, or theta, are 0 as well. And so we're going to start with cylindrical coordinate Navier-Stokes in the x direction, right? Navier-Stokes momentum in the x direction looks something like this. And so, this looks like there's a lot here, but we're going to drop out most of these terms, right? So for example, let's see, where do I start? Oh, there's more. Sorry. We have to expand this operator as well, right? So we expanded the operator, the Laplacian, right? This del squared of v. We expanded that out as well. And just to remind us and orient ourselves from what we learned in chapter 4, this is the time derivative of velocity, right, with respect to time. These terms here, what are these terms here? Somebody just shout it out, it's fine. Advection of momentum, advection of x momentum, right? So this is just what that looks like in cylindrical coordinates. But we can see some familiar faces here, right? So VR, dvx, dr. This would be advection of x momentum in the r direction. In this case, it's going to be 0 because VR is 0, right? But these are the advection terms. This is our pressure term. One thing I want to draw your attention to here is that we have this, total derivative, or this dp different. We're using a different derivative indication here for dp dx. This is not the partial derivative of pressure with respect to x. Pressure is only varying in the x direction. And despite the fact that we are fully developed, the pressure does vary down the length of the pipe. Okay, that's why we're using a different derivative symbol here. It's the main reason why we're using a different derivative symbol here. So fully developed means the velocity profile is unchanging down the pipe, but the pressure can vary down the pipe. In fact, we think of pressure as being the primary driving force for this flow. The pressure being higher upstream and lower downstream is what's pushing the flow through the pipe, right? Imagine blowing on the end of a straw or something. You're using pressure to push the air through the tube, right? The similar kind of thing is happening here, and that's captured in this dp dx, which is non-zero in this case. Yes?
And is that change in pressure only caused by like I mean, I know like high pressure, low pressure, but you have to get from high to low, right? You have to do that whole loss.
Yeah, that loss is friction. So the question is, what is causing that change in pressure? And the answer is yes, it's a change in pressure due to frictional losses. Right, we're going to see that in Navier-Stokes actually. So after we drop everything out, we're just going to be left with a balance between pressure and friction. Right, we're going to get a very simple form of Navier-Stokes, very much like what you saw for flow between two flat plates. And we see this in the energy balance as well, where there's a trade-off between head loss due to friction, right, which is captured by viscosity, right, which is driven by viscosity. This mu here is kinematic viscosity, mu over rho. So the head loss due to friction is driven by viscosity, and that causes a pressure drop if we look over two sections in the pipe, right? So yes, exactly. So the pressure is decreasing because of frictional losses. That's exactly right. Okay. Any other questions? Right, and then just moving further, we have our gravitational acceleration term in the x direction because this is the x momentum. We're going to assume that's 0. And then we have this term, which describes the frictional effects in the flow, nu del squared Vx, expanded, and that del squared Vx term is expanded out here. These are all second derivatives of velocity with respect to different coordinates. Gets a little bit more complicated in the r direction, but not terribly much. These describe the shear forces within the fluid, the frictional shear forces within the fluid. Okay, so we're going to start dropping things out of this. There we go. So ddt is 0 because we're steady state. Vr is 0. V theta is 0. dvdx is 0. So this entire left-hand side dropped out. Gx is 0 because we're ignoring velocity, we're ignoring gravity. And all the way on the right-hand side, we have d squared Vx d theta squared is 0 because we're assuming it's axisymmetric. There's no variation around the theta direction. And d squared Vx dx squared is 0 because again, we're assuming that it's fully developed. So we've simplified this dramatically. And we're going to rewrite the simplified form on the top of the next slide if you're taking notes. Give a second. Okay. So what we're left with is this. And now I've just taken, and that's the wrong D for the pressure. That should be, it is not the partial derivative of pressure with respect to X. That should be, that's a typo. That should be like the normal dP dx. We've moved it over to the other side. Right, remember there was a negative sign when it appeared on the right-hand side. That came all the way back from the fact that we defined pressure as being positive in compression. Anyway, we pulled it out to the left-hand side, and now we have dP dx is mu 1 over r partial with respect to r of r partial of Vx with respect to r. So now we want to solve for Vx. What can we do here from homework 1? What's our next step? Integrate. Yeah, sorry, you have to speak up a little bit because this thing is still blowing. Yeah, so we're going to integrate, right? So this is, we're going to say that dP dx is constant. The pressure gradient with respect to x is going to be a constant. It can vary from one pipe to another, but within a given pipe problem, we're going to assume that the pressure gradient dP dx is a constant number. And then, so we're really just trying to find this V. Yep. You're correct. There should have been a 1 over rho. Yeah, let's go back. Here, this is where it went. It was minus 1 over rho dP dx, right? And this V is nu over rho. Yeah, this nu is mu over rho. Sorry, this nu is mu over rho. Yep, sorry, not V. This is nu. So this is the kinematic viscosity, right? Has units of meter squared per second. And it's our basically like diffusivity of momentum, and it's mu over rho. Okay, you're welcome. For a second, I was worried. Okay, and now we need boundary conditions, right, to apply this equation, right? Our boundary conditions are going to be no slip at r is equal to r, right? So if the pipe is stationary, that means the velocity is 0 at the big radius, big R, right? At the radius of the pipe. We have this other weird boundary condition which pops up a lot of times in cylindrical coordinates or spherical coordinates sometimes, which is we apply it at r is equal to 0. We're going to say that we need a finite velocity, and we'll see why when we go through the next couple steps, why we need to impose this condition. But that's our second boundary condition here. It's a little bit of a non-standard boundary condition. Okay. So we integrate twice, and we're going to end up with this expression. So Vx is dp dx. Corrected that here. R squared over 4 mu plus C1 natural log of R plus C2. And now we're going to impose our boundary conditions to find C1 and C2, right? And that second boundary condition. So if we look at the natural log of 0 goes to infinity, and we cannot have a velocity that's going to infinity at the center of the pipe. And so we know that C1 has to be 0. Okay. See some confused looks, but we cannot have an infinite velocity, right? That would be bad. So and non-physical. So we know that C1 has to be 0 because this velocity, this expression should give us a finite velocity. Oof. Okay. So we apply those boundary conditions, and we end up with this expression for Vx. Typically written this way: minus dp dx 1 over 4 mu big R squared, that's the radius at the outer edge of the pipe, minus little r squared, that's the radius at which we're evaluating the velocity. So our velocity profile is parabolic. It's axisymmetric, so this is like a paraboloid, like if we take that thing and imagine rotating it around the axis of the pipe, that's what the velocity looks like, right? We have this like parabolic shell thing is the velocity profile that we've developed for laminar, fully developed flow within a round pipe. Okay. So now that we have this, we can use it in order to find other parameters about the flow, right? So we can use this to find, for example, the average velocity within the flow. We can figure out what the maximum velocity within this pipe flow is, right? And important for figuring out the friction factor, we can figure out what the shear stress at the wall is. And that's actually gonna allow us to find the friction factor for laminar fully developed pipe flow. So if this is our Vx, so we can say dpdx is the pressure gradient that's driving the flow. Sometimes you might see this expressed as delta P over L, right? It's really like the drop in pressure across some length of pipe. You know, if we know the pipe length L, it's the drop in pressure across that whole pipe. So we can find V max is going to be V at the center of the pipe, or R is equal to 0. Right, so if R is equal to 0, then we have the maximum velocity is minus dpdx 1 over 4 mu times big R squared, right, the maximum velocity within this flow. And we can find the other parameters like V average, 1 over area times the integral of Vx dA. You know, again, this comes from discussed in chapter 3, but we can evaluate this for this flow. So R squared delta P over 8 mu L. If we evaluate that integral. Q, right? The overall flow rate, the volumetric flow rate through the pipe. It's just the integral of Vx dA, or A times V average, right? So we can find the area of the pipe and multiply that times our expression for V average and develop an expression for Q, the volumetric flow rate. Not shown here would be the mass flow rate, which we typically write as m dot, right? That would be rho times Q or rho times V times A. So this times rho would be m dot. And finally, we can find the shear stress at the wall, which is what we're going to need to develop the friction factor F. And our shear stress in a Newtonian fluid, mu times the derivative of velocity, the spatial derivative of velocity. In this case, if we were to look at the definition of the Newtonian stress tensor, the only term that would be remaining would involve this dvx dr. That's the only non-zero terms in that entire stress tensor. So again, it looks complicated. Remember back when we were discussing tensors way back in those chapter 4. Looks very complicated, but most of the time, a lot of those terms drop out. In this case, this is all we're left with. And so the shear stress at the wall is this expression evaluated at R, right? The location of the wall. And we can find that as R delta P over 2L. Yes. Yep. R is equal to 0 is the center of the pipe, right? Because we have a cylindrical pipe now, and R is pointing outwards from the center. Yep. Yes. Where did the 8 come from? Sorry, where? Here? Oh, sorry. What's that? Oh, that came from integration. That came from our integration of with respect to R. So if we expand out dA, then we have 2 pi r dr, and we're going to end up with a factor of 2 that comes out on the bottom of that, which went from the 4 to the 8. Yeah. Without. Yes. If you find that's incorrect, let me know. Okay. Yeah. It could be. Okay. Any other questions? Okay. It's like static electricity. Fries my computer every time. Okay, so from the definition of friction factor, we know that head loss due to friction we defined as F L over dV squared over 2G, right? That comes from that 19th century relationship derived in the 1800s. And we know from momentum balance that we discussed last class, we can also write the head loss due to friction in terms of that tau wall. And now we know tau wall for a laminar pressure-driven flow, right from the previous slide. For a given problem, we're typically going to know like L and D, and let's say we know V. So what we're left with is solving for the friction factor F within this system, right? So, and this V here, I should note, we're going to denote as the average velocity. So V is also going to come from that previous slide, right, where we're going to plug in an expression for average velocity. So from this, if we put it all together, we'll end up with F, friction factor F for laminar flow is 8 tau wall over rho V squared. We found average velocity and wall shear stress on the previous slide. So here we'll actually go through the how to find V, right? So we have the expression for it on the previous slide. We have 1 over A, integral from 0 to R of our velocity profile, right? Vx times 2 pi r dr. This is dA, right? Right. So just as a reminder, we're looking down the barrel of the pipe. We're going to integrate with respect to we're trying to integrate with respect to area, right? Or dA, and our differential area is 2 pi r, right? Like the circumference of the circle, times the differential thickness dr. So that's our dA. Came out over here. And then and this evaluates to V is minus dp dx r squared over 8 mu when we go through the full expression. Really, yeah, you can see here where that's going to come from. So we're going to end up with an r squared times r, right? And when we integrate that with respect to r, we'll get a so we'll have a little r right to the first power here, and then that little r will be raised to the second power times 1/2, and that's where we're going to get this this 8 from the 4 to the 8. That makes sense. Yeah. Okay, so have our V average. Tau wall mu dvx dr at r is equal to r. So again, to expand this out, this would be mu ddr of our velocity profile, and we're going to evaluate it at the full radius of the pipe. And so we have tau wall is r over 2 times, in this case I'm writing it out as the magnitude of dp dx. Okay, to avoid confusion with the negative sign. And now if we plug this back in, we're going to end up with friction factor F. Remember, it was 8 tau wall over rho v squared. We just get this expression here, 64 over Reynolds number based on diameter. Once we've evaluated what's or plugged in our expressions for tau wall and V, and use our known definition of Reynolds number. So friction factor 64 over Reynolds number based on diameter. So this is what's plotted here, right? For the laminar flow regime, this is the 64 over Reynolds number is what's plotted for our friction factor. One thing I want to bring to your attention is that was on there the whole time. Okay, that answer was on this plot the whole time, and this plot, this Moody plot, is something that I'm going to give you on exams. It's a standard reference material, a standard piece of reference material for solving pipe flow problems. And there's an enormous amount of information that is contained on this plot. For example, the solution to what we just spent 20 minutes or so discussing is right here, right? So F is 64 over RE. So on an exam, you encounter that question. You don't have to go flipping through your book, just go to the Moody chart. Okay. The definition of friction factor in terms of H, right? In terms of the head loss due to friction is on here. So that means I could actually take this expression here and rearrange it, right? As like, let's say I have a problem where I'm trying to find the head loss due to friction. And you look up friction factor. Let's say you compute it for laminar flow 64 over RE. And now you need to know what the head loss due to friction is. You can just rearrange this expression and say that H is equal to F times this thing, L over D V squared over 2G. All right, so that key equation is right here. Another one down here, Reynolds number, Vd over nu. So this is now expressed in terms of the kinematic viscosity, right? Instead of the, the mu that we might be more familiar with. But Reynolds number is down here as well, right? Up top, you can see values of V times D for water at 60 degrees, values of V times D for atmospheric air at 60 degrees. So if you know the velocity and the diameter, right, the velocity of the flow and the diameter of the pipe, and you're considering air or water, then you could use that to more or less very quickly figure out where you should be on this plot. You also use that to figure out Reynolds number, right? Without having to look up your viscosities. So I guess those are in feet per second. But if you knew VD in feet per second, it was 20. You could just read that down and come up with your Reynolds number of maybe 18 times 10 to the, or 1.8 times 10 to the fifth. Your definition of relative roughness is on here, right? Epsilon over D, along with some different values. In addition to that, there's a this is telling you roughly where the cutoff is for transition, for the start of transition to turbulence. Is again somewhere around 2,000, 2,300 Reynolds number for internal flow, right? So that's on here. You have to be a little careful when it says transition zone. It means something different than the transition to turbulence, and we're going to talk about that when we talk about turbulent flow. But this, when it says transition zone, it's referring to something other than transition to turbulence. It's transition to what we're going to call fully rough flow in pipes, and that's something slightly different. But the transition zone is on here, right? Transitional Reynolds number, a transition to turbulence zone is indicated on here by this kind of light blue region. Yeah, question. Epsilon is typically going to be a property of the pipe material. And yeah, we're going to have a table of epsilon that would be on the exam. Yeah, or would be given to you. It can definitely vary. If you have like new steel versus old steel, you're going to have different roughness, right? Depending on corrosion and pitting and that kind of thing. So it can vary over time, even within the same material. But yeah, typically that would be known, or it would be measured. There might be a handbook of values at a company or something for their own characterization, right, from their own characterization. Yeah, so this would be our transition to turbulence region. And it tells you some things about the characteristic of the flow in the turbulent regime as well, which we're going to talk about when we talk about turbulence. So I just wanted to point out that this plot that I will give you on the exam, and that is also at the back of your textbook if you have the hard copy. It's just like open up the back cover, I think it is right in there. Has answers, or can help you find answers to many of the types of things that I might be asking you. Okay. And they're right here if you know how to read it. Okay. Yeah. Yeah, so this is a logarithmic scale, right? Because Reynolds number is varying over many, many orders of magnitude. So we plot this on a log scale. And that allows us to capture things from, under 1,000 all the way up to 10 to the 8th, right? So almost 1 billion, right? 100 million. So all on the same plot. Yeah, so you do have to get a little bit accustomed to reading things out in terms of those numbers. Yeah. Okay, but we're going to see this a lot, and a lot of times the question, or a question I get from students is like, why would we use this, right? Because for example, we have equations, right, and we're going to have some equation like approximate curve fits out here as well, and those are definitely useful. But there's an enormous amount of information on this plot if you know how to read it. Okay, so we're now going to move through this plot. We're going to avoid talking about too much about what goes on in this region, the transitional region. We say there be dragons, right, where we're transitioning from laminar to turbulent flow. We'll talk a little bit about what happens during transition to turbulence, but and maybe give an idea of why things get more complicated in this region. But the next step on our journey here is to figure out what's going on with all of these curves. Like, what do all of these different curves mean? Where do these things come from? And in order to do that, we're going to have to talk about modeling. We're going to have to talk about how we model turbulence using what we know, how we can develop models that can approximate what's happening in turbulent flow. And so for the last 10 minutes or so today, we're going to introduce this concept of turbulence modeling. Then we're going to pick up with that on Friday after some videos to develop this a little bit further and get us towards the Moody chart for turbulent flow. So, so we use the Navier-Stokes equations for laminar flow. Navier-Stokes equations definitely describe laminar flow. They also describe turbulent flow. You know, so this set of equations still applies. It's just that we cannot easily solve them like we did for laminar flow, right? So in the laminar flow case, we were able to say that a whole bunch of derivatives were equal to 0, and a whole bunch of terms in Navier-Stokes equations dropped out. We can't do that in when we have turbulent flow. So one idea of why that might be, you can actually kind of see in this movie here. So we primarily have flow from left to right. So we primarily have flow, let's say, in the x direction, right down the screen. But because of that flow and this turbulent flow, we have the formation of eddies, which are creating smaller eddies and smaller eddies still, all the way until they're dissipated by viscosity, right? So we have eddies across a large number of length scales. And those eddies are these little vortices within the flow that are created by the flow. And those vortices are creating velocities, not only in the primary direction, right? In this case, down the board that we're concerned with, but also in the, you know, let's say the z direction, moving up and down. And if we were to look at this, this is actually going to end up as a 3-dimensional flow. It's also creating eddies in the direction into and out of the board, which we just can't visualize here. One of the fundamental problems here is that turbulence can create velocity fluctuations, or even though we have a primary flow in one direction, turbulence will create velocity fluctuations, gradients in velocity in all 3 spatial dimensions that vary in time. So it's not even strictly steady. And so so, you know, we can't do the same nice things that we did with Navier-Stokes where we dropped out a whole bunch of terms. We basically have to keep all those terms. And that's one of the things that makes dealing with turbulent flow so challenging. But we can approximate this, or we can make some headway towards approximating this by looking at the velocity, or basically what we're going to do is split the velocity into 2 different pieces. So if we look at the velocity at some locations, so let's say we're looking at velocity in that little box up there within this movie, and we measure the velocity there as a function of time. And I'm just going to measure the velocity, the x component of velocity, u. But I could do the same for v. I could do the same for w. Let's say we look at u, right? The x velocity there is a function of time. What I would see is, you know, some noise, right? Some fluctuations in velocity. But in this case, right, the flow is primarily in that x direction. And so there's also all of those fluctuations are superimposed on a mean velocity. So I'm going to denote that mean velocity as u bar. So it's the average velocity at that location, time average velocity at that location. And then I'm going to say that the rest of it, the fluctuations around that mean velocity, I'm going to call u prime. So basically taking my velocity that I measured as a function of time, u, and splitting it into u bar, the time average, plus u prime, the fluctuations around the time average. Okay. So I have these 2 components. Now what this lets me do, this is going to help me to develop some turbulence models where I'm going to try to predict the behavior of the time average velocity, and try to account for the impact of by accounting for the impact of these fluctuations in velocity. And there was a question. Okay. So core to this concept of splitting, right? So now we're going to split our velocity into these two components, the time average, in this case, U bar, and the fluctuation component denoted by prime. So I'm going to split the velocity into two components. And one of the primary motivation for this is that most of the time, like if I'm, let's say, doing a computational fluid dynamics, a CFD simulation of this jet, right, this turbulent jet, because I'm trying to design, the nozzle that's going to be expelling this into a tank or something. For the most part, I don't really care about the details of the fluctuations, the prime part here. For the most part, all I really care about is the average, the time average velocity, or the time average velocity profile. So so by splitting the velocity this way, we're basically saying the actual velocity within the flow is the thing that I really care about in most engineering situations. And this other thing, which is hard to deal with, but I'm going to see if I can develop some empirical way to get around that. Okay. So that's the core concept here. We call this time averaging. Another example would be like when we're looking at pipe flow. I don't really care about all of the turbulent velocity fluctuations in the velocity profile within a pipe. If I'm designing a big pipe network, all I really care about is the average velocity, the average frictional losses. That's going to be good enough for me to do my design work. So splitting, so this is just like expressing in math that the only thing I care about is that time average piece. And we're going to follow that through the Navier-Stokes equation. So in 1895, Reynolds number fame, proposed what we now call Reynolds averaging. So what we basically do is we define the time average, U bar, as 1 over t, some time period t, interval 0 to t of u with respect to time. So it's basically just the average of the velocity over some time period. It might be like the time period of observation or something. And with that, one thing to note, this is an operator, so we could apply it to any variable. So if we had some variable beta, we could do the same thing and have beta bar. Right here we had U bar. We could have beta bar, V bar, W bar, P bar, right, pressure. So this is a general operator. And so we're going to apply this then to Navier-Stokes, noting that each variable within Navier-Stokes is going to have both average and fluctuating components. So for example, U, right, we're going to split into U bar plus U prime. The same for V, same for W, same for pressure. Where this is the average and this is the fluctuation. And then our goal is going to be to take the Navier-Stokes equations and try to write a new form of the Navier-Stokes equation, which is going to be time averaged, right, in a sense. So we're going to try to write a form of Navier-Stokes where the only thing that we deal with are these time average quantities, like the overbar quantities. And the results of all of this are going to be what we call the Reynolds average Navier-Stokes equations, or RANs. These are, and these equations are going to be what we can use to understand the average influence of turbulence on flow, which again, from an engineering perspective, is mostly what we care about. And these equations are widely used in CFD, right? So the work that we're going to do on Friday, just about out of time today, is going to be to develop a new form of the Navier-Stokes equations called the Reynolds average Navier-Stokes equations, or RANs equations, or RANs, that are going to basically be what you're using when you're doing CFD of turbulent flow. Okay, so that's what we're going to pick up on Friday. Thank you all, and I'll see you then.